The purpose of this project was to design an aircraft. Since we chose an airplane to design, we had to specify aspects such as the wing dimensions and the type of engine. From this project, we hope to achieve a better understanding for flight calculations such as the force of drag, force of lift, and thrust, and experience what it's actually like to design an aircraft.
When choosing our airfoil, we started by looking at the differences between most conventional airfoils and the differences between 4-digit, 5-digit, and 6-digit airfoils. We found that the most popular design for our style of aircraft was the thicker structures that had a good characteristic of camber along the chord length, and it allowed for increased lifting capacity across the whole entire wing while also maintaining a low amount of drag. We decided to choose a 5-digit airfoil, the NACA 63-412. We found the efficiency increased with turbulence, which is very important for us. At our altitude and speed, we're looking at a very high Reynolds number due to the high amount of turbulence. We need a large efficiency for this as well, and we found that this airfoil provided that because the efficiency increased with the Reynolds number.
Calculating the size of the wings required a few assumptions to be made and a couple procedures required to assure a successful takeoff but also a successful cruise. The diagram on the left gives a little insight into the steps and assumptions our group took to confidently determine our wing size. An initial assumption had to be made about the angle of attack at takeoff, which was decided to be 12.5 degrees. With the angle of attack decided, our coefficient of lift could be properly calculated as well through the max takeoff weight. Through that value, our lift equation only had one unknown, which was the minimum wing area required. This minimum wing area just calculated was incredibly important because calculating our wing size based off the cruising specifications would have made it such that the takeoff would have been impossible. By calculating it instead at takeoff, it ensures that it will provide both functionality at cruising and takeoff conditions. With the minimum wing area and our initial lift equation, the only remaining unknown the second time around became our coefficient of lift, which helped determine the required angle of attack at cruise.
The next value that needed to be calculated was the force of drag. This is calculated the same way as the force of lift, except the coefficient of lift is replaced with the coefficient of drag, and the force of drag on the fuselage needs to be accounted for. For the force of drag on the wings, we use the same area that was calculated in the previous slide, and the coefficient of drag was found via the coefficient of drag versus angle of attack graph. For the fuselage, the force of drag was based on the area provided by the Boeing model. This had to be calculated at two different positions, cruising altitude and takeoff. This was due to the fact that at those two positions, there's a different air density, different velocity, and a different angle of attack. The force of drag was used to find the power by timesing it by the velocity of the plane. The power is based on the power needed to overcome the force of drag. Based on the power, we decided that a turbofan was the best option because the power was so big and needed a huge jetliner engine to power it.
For CFD analysis, we wanted to compare the reference data we got from the airfoil tools that they simulated off Xfoil to our simulated CFD data for our project. Basically what we did, we started with the typical CFD procedure where we took our airfoil geometry, uploaded it into ANSYS, create a fluid domain that's relatively large compared to the airfoil so we can get a good amount of capture of what's going on. We started with our mesh, and the mesh density was very high around the tips of the airfoil to provide a good idea of what's happening around the airfoil in terms of disturbance and its lift and drag characteristics. So basically once we got our mesh, we went to our solver and we started with an analysis of our solver methods. So basically ANSYS has two different types, ANSYS Fluent has two different types of methods, a density and pressure method. The density method is used mainly for higher subsonic Mach numbers and is used with compressible flow, while the pressure method is used for incompressible flow. We found that the difference between these two in terms of our project, we did a test on both of them and found that the density method took a large number of iterations and didn't necessarily converge to a nice value. It would oscillate, and the pressure method instead would converge very quickly to a nice value with under 250 iterations. So for this project, even though it might not be applicable for what our conditions were at cruising altitude, for the simulated stuff, we used the pressure method. So basically what this involved, we would solve the Navier-Stokes equations and then post-process all this information into comparing it to our reference data. So the graph you can see there is a comparison of the efficiencies for our CFD data, which we had a Reynolds number of around 70,000 compared to a 1,000,000, 50,000, and 100,000 that airfoil tools gave us. And then on the right-hand side, you can see the velocity stream, post-processing images, and the pressure contour plots.
Due to the reference plane that our group used being a 747, the history behind how that plane came to be and the involved technology was a pretty interesting topic for us to explore. On September 30th, 1968, the first Boeing 747 was complete and representatives from over 25 different airlines were there in attendance. This new airplane covered a wide range of technological advancements, but the first one that it did was called the fault tree analysis, which relied heavily on redundancy throughout the aircraft, and which set the standard for the modern day safety requirements that commercial airplanes use today. Not only were the safety systems incredibly important, but the engine inside the plane was at the forefront of technology, in which Pratt & Whitney and their JT9D engine won the bid and helped supply thousands of airplanes throughout its lifespan.
Here are our final results. Thank you for watching.